All right, lesson 113. This is the last lesson for unit one. What we're going to do today is we're going to tie in a lot of stuff with calculators. Like today is a very important lesson that you learn how to use your calculator correctly for problems you're going to see throughout the school year. So our learning goal, we can identify an appropriate function type to construct a function model for a given scenario, and we will use the calculator. I should have put this on there. And we will use the calculator. Let me just type it in. How about that? And we will use technology to create the appropriate function model. So this is what we're going to be doing today, okay? So as we go through, you're going to see me use the calculator. We're going to determine which model is appropriate. And then after we decide what's appropriate, we'll find the equation that models the appropriate type of equation. All right, so that's the plan for today. I don't know why it's not letting me cover that up. There we go. Cover up that period. And that's our learning goal for today. All right, so let's get started. On this slide, this is for when you're doing homework. I have some Delta Math problems where you have to do this function model. And at home, you don't have my calculator. If you scan that QR code, it's really easy. You'll enter the table and you'll choose what model you want. That code is going to be very helpful for you for your homework. It works really well. I created it, spent a lot of time on it. You'll figure it out real fast. All right, so first, the idea of modeling, what we're going to be doing today, meaning given data, we're going to model the data with an equation. They're not going to give us an equation today. We're going to come up with an equation. That's what we call a model. The idea of model or regressions is a major component of the pre-calculus curriculum. Okay, and so you can read over that. But specifically in Unit 1, we're going to be doing polynomial and rational functions. As the school year goes on, you're going to see exponential, logarithmic, trig functions, all different types of functions, but specifically right now, we're going to be looking at polynomial and rational data, okay? So first, let me give you an example, and we're going to talk about what type of models we could be using when they don't ask us to do so. So first, the age in weeks and weight in kilograms of 5 randomly selected babies in a particular pediatrician's office are listed in the table below. First, write the equation of the linear model for this data. So I want to walk you through how to do this. I need to shrink my screen here. So take your calculator, press home button, new document, don't save. Now this is very important on models that you do a new document every time you have a new model because the calculator is going to create some variables for us. And when you go to new document and you choose not to save, it erases all the old, which is very essential for you so you don't get a mistake where you don't want the calculator to use old data. So make sure you clear it. I want you to go to Listen Spreadsheets. Now, when we get to Listen Spreadsheets, what I want you to do is title your data columns up at the top. Now, this one is they use a T and a W. You don't have to put W or T, just put T and W. We could use X and Y, but I'm going to use T and W. T and W. You could use X and Y. I'm using T and W. And now I want you to type in this data as we go down. So we have, for the T column, we'll have 4, 5, 6, 8, and 12. And then for the Y column, 4.2, 4.4, 4.8, 5.1, and 5.7. Now, once you get your data in, there is one thing on my calculator that can get really tricky. Can you look at my screen here? Let me make sure you can see it full screen here. If you're clicked and you see that cursor right there, if you've accidentally clicked on a new cell and you have a cursor, the menu buttons won't work right. So you need to make sure you just move your cursor where that you see, move the box so that the cursor is not there. You see how there's nothing flashing there, no vertical line. For this to work, just make sure you've moved off or you don't have a cursor. If you leave it 5.7 with a cursor, menus won't work. I'll show you. I'll press the menu button right now. We're going to go to 4. Everything's grayed out. Can't click anything. So what I want to make sure you do so that your calculator works right is just move your box. You can just move it off or press enter, whatever you want to do. Just make sure the cursor has disappeared. As long as it's disappeared, you're good to go. All right, from here, they tell us to make what type of model? Linear. Since they say to use linear, here's how you do that. I want you to press the menu button, choose number 4, statistics. Then we're going to go stat calculations, and from there you're going to see a host of models, a whole bunch of different models. Which one are we looking for? Linear. There's 2 different options. I would suggest doing the linear regression mx plus b, because that's going to be slope-intercept form, which you're used to, y equals mx plus b. Click on that. Now this x list means you need to tell the calculator which variable is your x. Which one's your domain? Is it t or w of t? T. So put a t there at the top. And then the y list is we put in the variable that represented the y. Now what do we put for y? W. Now again, if you had used x and y, you would just type x and y there. Now here's what I'm talking about earlier. It's going to start saving information, and see how it says it's going to save the equation to F1. If you cleared a calculator like I did, everyone's calculator should say it's saving it to F1. Go ahead down and you hit the OK button. You can just go down this way, hit the OK button, hit enter on that, and it'll give us our equation on the side. Okay, so here's what I got. Did you get the same values as me? Where if you look at where it says M, just to the right of M, it has 0.8185. Did you get that value? And a B of 3.545. Did you get that? Yes? No? Okay, so this is our model. So our model, we're going to call it like this. Remember, this was the X value. X is equal to T, Y was equal to W2. Here's what that means. You're going to write the equation like this. You're going to say W of T equals, remember the formula is M times X plus B. There's the formula right there. It's on your calculator. You can see it. You put the M value, 0.185, times the X value variable. What is our X variable in this problem? T. So you put a T plus the y-intercept, which is 3.545. So that's how you would write your equation. You use the same variables they gave you. You use the same variables they gave you, and you would write your model like that. So this is the model W. So from here on out, if I say model W, I'm talking about this equation that we just came up with. Did they give us that equation? No, we modeled the data with the equation. Okay? Part B. Am I going too fast? Are you with me? Anybody struggling to get those values in the calculator? Everybody got it? Everybody's good? Okay. So part B, what are you going to have to do with that data? It says using the linear model from part A, what is the predicted weight of the baby that is 10 weeks old? Now, some of you know the math very, very simply how to do this. I'm going to show you calculator tricks because as we go on through the year, the equations are going to get very complex. So we're trying to find the weight of a baby that is 10 weeks old. What is 10 weeks old? Is that a weight or is that a time? Okay, that's saying T equals 10. So what we're going to do is we want to know what's the weight when the T is 10. Does that make sense? What I'm trying to find? Let me copy this equation so you can just look back and forth, but since my slides aren't back to back on mine, here's what I'm going to do. I'm going to substitute a 10 in. Where do I substitute 10 in? Okay, good. Y'all are right on board here. This T value and this T value are going to get replaced by 10. Now, I'm going to show you how to do this in the calculator so you never make a mistake. You ready? Very important slide here. I'm trying to find that value right there. That's what I'm trying to find. Here's how you do it in the calculator so you never make a mistake. Press Control and then hit dock. Press Control and then hit dock. You can see up above the calculator it says plus page. It'll add a new page. I want you to add a calculator. So Control dock should add a page. Choose add a calculator. Have you done so? Now remember how when we were doing that stat calculation, I showed you it was going to save the data to F1. What I can do here is I can type in F1. When you press F, you'll see it's an italic F. When you press 1, though, it changes to bold. You see how I did that? That's taking the data. It knows what the equation is. It saved it. And then I want you to put parentheses 10. What this will do is the calculator will plug in 10 into the equation that we just found. Press enter. Did you all get 5.9? All right, 5.35? That right there is the predicted weight at 10 weeks. That right there is how you would do that. Okay, let me just shrink this in for the notes. That's how you would find that. And so the weight at 10 weeks, would be 5.395. And what is that in kilograms? Is that what it was? I forgot. Kilograms, yes. Or maybe I should just write it in using English words. The predicted weight at 10 weeks is 5.395 kilograms. That's what we just discovered in the calculator. Okay, so again, why I suggest using your calculator on that is because you'll never make a typing error. If you just let the calculator, even if you wrote it down the wrong the first time, the second time you should get the right answer if you use that window. Okay, now next. It says the weight of a sixth baby is 5.3 kilograms. Using the model from part A, what is the age of this baby? Okay, so this time, what did they give us? They gave us a weight, which as far as the variables go, this is saying the weight is equal to 5.3. Do we know what the time is, though? Do we know what the time is? No. So how we would solve this is instead of having W of T here, let me copy or paste my equation again. It's not pasting. Okay, let me copy it one more time. This time, here's how I would solve that. Is in the equation, I'm going to replace something. What am I going to replace in this equation this time? WT. What's WT get replaced with? 5.3. And now here's the deal. We could solve this by hand, but anytime you're doing regressions, it's going to be a calculator question. So I'm going to make sure you know how to solve in the calculator. It's a way to make sure you never get this wrong. So I'm going to solve this in the calculator. So how do I do that? Press menu 3-1. And we're going to type this equation in. So menu 3-1 is what I press. We're going to type in 5.3 equals 0.185 t plus 3.545. And then you'll do comma t. The comma t tells the calculator what it's solving for, and also what it does with insolve is even if you have data stored in as t, it clears just for a moment to solve that. So type all that in, press enter. What do you get for the predicted amount of time to have a baby that's 5.3 kilograms? What are y'all getting?
4, 3, 5, 3, 5, 5.
Ooh, I got a different value. Okay, check yours again, Giovanni. See where you messed up there. Did you find your error?
Yeah.
Okay. So this is our t value. So to solve this, our t would equal 9 point, and I haven't told you this yet. In AP pre-calculus, you're supposed to round to 3 decimal places. You can round it or you could just cut off the decimals. I suggest we just cut off the decimals because you'll never make a mistake. If you round wrong, they'll count it wrong. But if you just cut them off, you'll always get it right. So take 3 decimal places. So what 3 decimals should we use? 9.486 weeks. I'll write it in weeks. That's the time. So the predicted age of a baby weighing 5.3 kilograms is 9.486 weeks. Okay, that's what the calculator gives us there. Now, I have a note in here from here on, I don't want you to clear the data here. We're going to save this so we keep it as F1. We'll return back to it in example 5. So just don't clear it from here on out. This one anyways. We'll talk here in a little bit. Let me mark this down this way so it's a little easier to read. There we go. Okay, so that's how you use your calculator. I just showed you the tools we're going to be using all throughout the year. All that's going to happen different is we're going to have more complex models. All right, so let's now go on to example 2 here. In example 2, it says the table gives the values of average life expectancy in years for a child born in the United States. Write an equation of the linear model where t is represented by the birth year. T0 is the year 2004, and L of t represents the life expectancy in years. Okay, so when you see that T0, what do you think that means?
Start.
That's like the starting. So, and when it says 2004 for the year, we're going to use this as like a t value, and we're going to say this is year 0. I'm going to make like another box here. You know what? Let me just make it clean. That's just going to look so ugly. Let me make a new box here. And what we're going to do is we're going to find each of the time values, and then we're going to use our calculator to solve. All right, we ready? So this is saying T0 is the year 2004. That means we're going to make that be time 0. So what does that make 2008?
Year 1.
Not year 1. Nope.
2.
Nope, not year
4.
2. Year 4. Why 4?
Focus go.
It's gone 4 years, okay? What would that make year 2012? 8. That's 8 years past 2004 or 4 past 2008, okay? What about 2016? 12, 2020,
16.
2023. 19, you got it. Okay, so on our calculator here, I want you to press home screen, new document. I want you to hit new. It's going to ask if you should say, what are we going to click this time? Yes, because we're going to come back to it. Hit yes. Mine's going to save it as document 1. Just pay attention to what it saves as, okay? You can do document 1, hit save. Now we're starting back fresh. All right, so where do we go first? Do y'all remember where do we go when we see a table like this? Listen, spreadsheets. They're using the variables t and L of t. So I'm going to go up top and put a t here, and then I'm going to put an L in the next column. So I'm going to use t and L. My times are 0, 4, 8, 12, 16, and 19. And then you can see the life expectancy. 76.75, 77.38, 78.19, 78.86, and 78.87. I missed one. $78, $79, $78, $86, $78, $87. Okay, I think I got mine now. Remember, just make sure that you don't see a cursor. So you can just move around your box so you don't see that cursor, and we should be ready to go. Okay, what type of model did it say to select this time?
Linear.
Linear. So once again, am I going too fast if I go now? Press menu. Stat calculation or statistics, then stat calculations, and choose linear one more time. I'm going to choose the linear that's mx plus b. For x list, what do we title our x column? T. For the y list, what do we title the y column? L. What's it saving the equation as? It's going to save it as F1. That's right. Okay, hit OK. And now here's my equation. By the way, I didn't talk about this before. The r squared value, if you go down here, that tells you how accurate of a model it is. And if you think of it kind of like a percentage, this is saying it's approximately 89.7% accurate, which means it's not actually that accurate of a model. For a lot of classes, is anybody in here taking AP statistics? They're going to require you to get a number at least 0.9, a lot of times 0.95. So this would not be that accurate of a model. But here's the equation we came up with. This is our slope. That's our y-intercept down below it. And like I said, that would be telling you the accuracy there, that 0.89. It's not the most accurate of equations you'll ever see or models. Which what that would mean is that you probably could select a different type of equation and that's not linear and get something more accurate. But this problem, they want it to be linear, so I'm gonna, oh my goodness, it goes so small. All right, there's my equation there. So if I was gonna write the equation, you're gonna call this is L of t, this was L of t. So we're gonna say L of t equals the slope I'm getting, again, 3 decimals. So 117 t plus, oh man, what's that? 76 point, I'm looking over here, 988. Is that what you have on your calculator if you go 3 decimals? To the nearest thousand? Could y'all speak up for me? Is that what y'all are seeing on your calculator? Okay. So that's our equation. And again, it was linear. We chose a linear model. So now, what does the model predict that the life expectancy of a child will be at 88 years? So here's your task, is you need to think through, is this an L value or a T value? When it says 88 years, is that a life expectancy or is that amount of time? So what year does the model predict the life expectancy of a child will be 88 years? So the life expectancy of a child will be 88 years. What is that telling us? Is that saying a year of 88? No, or life expectancy of 88. Okay, so that means L of t, whoops, L of t, the L of t value equals 88. So to solve this, we're going to plug that in for L of t and insolve. So we're going to say 88 equals 0.117 t plus 76.988. So from your calculator, do you remember what buttons I pressed to figure this out last time? Control dock, very good. Press Control dock. From here, we're going to add a calculator to insolve. What buttons are insolve? Menu, 3, algebra, 1, numerical solve. We'll type in this equation here. 88 equals 0.117 t plus 76.988. And then you'll do comma t. Type all that in, press enter. What do you get? 94.111. Now we need to make a simple adjustment now. It says what year? Does that mean it's going to be year 94? Would it be year 94? Would that make sense? No, when it says year, we're actually going to make the adjustment from t. So T of 0 is 2004. So if it's year 94, I need to take 2004 and add 94 years to that. So take 2004 years, and let's add this answer here. I'm going to press the up arrow to highlight it, and I'll press enter, it'll copy it. When I add that, what year do you get that the life expectancy will be 88 years?
2098.
2098. That will be the estimated year. Okay, so what we'll say here is that T is 94.119. And so when we take our the year would equal 2004 plus that 94 point. You know what? I'm just going to write it out in simple words. The model predicts that the life expectancy of a child will be 88 years in 2098. Now, do we need to do the decimal on a year? No, years you do a whole number, so you can just say 2098 like that, and that can be your answer. You could leave it just like that. And let me get my picture added in. There we go. So are you getting the hang of how to use the calculator? How we're going to use it to find values? Hopefully you're getting the hang of how to work. Now, so far I've only done what type of models? We've only done linear. Is every model we're going to see this year a linear, you think? No, absolutely not. Okay, so now let's get on to this residuals. This is how you can tell how accurate a graph is. Now, I told you that R squared value. The R squared, where you want it to be the number 1. I didn't tell you that R squared is perfect if it's number 1. Well, here when we talk about residuals, what this is going to show you is how much the predicted value is actually off from the actual. So here's what you need to have memorized, because this you'll see on calculator and non-calculator problems. A residual is the actual minus the predicted. So what in real life is more important? The actual event or what you predicted what would happen? Which one's more important? Actual comes first. You take your actual and you minus what you predicted was going to happen. Does that make sense? I predict I have $100. I only have 80. Which one's more important? How much you actually have. How much do I actually have? 80. You would take your 80 and you'd subtract what you predicted you're going to have. And so in this example, if I thought I was going to have 100, but I actually only have 80, I would take 80, I would subtract 100, and I'm left with what?
20.
Not 20. 80 minus 100,
Oh, negative.
negative 20. The residual would be negative 20. What that means is I predicted more than I actually had. That's why it's a negative 20. Okay, last thing on this. Here's the symbols you might see where it has y minus y hat. This is what you call y hat. This means the y itself is the actual value. The y hat is what you predicted was going to happen. So you can see those symbols. You need to know those symbols. Okay, what does y hat mean? Predicted. All right. So now let's look at some scatter plots so we can figure out what a residual actually means. Here, this slide here. Scatter plots and residuals can be used together to quickly identify how close or how much of an outlier a point might be. Outlier means off the predicted value. So for example here, the point f of 70, 21, equals 21, sorry. F of 70 equals 21. Let me pause there. What does the 70 represent? What does 70 represent? The miles driven. Okay, so you would go to 70 on the x. And then what does 21 represent?
Okay.
The price, which is in thousands, it'd be 21,000. This point right here, it's saying it's over 70 and it's up 21. Okay, so that right there can be quickly determined to be 5 units below the predicted value. So what does that mean? What is, if it's 5 miles below, what was the predicted value at 70? What was this predicted model right here?
75.
Not 75. It says below. 70 is the X. We're not going left and right. We're not changing that. So try again. 26. There you go. It's 26. Why is it 26? Because it's five below, and so you're looking at the Y values. So if 21's 5 below, what was it predicting it to be? 26. There you go. That's the prediction. Just so you know, this is the prediction. The prediction was 70, 26. This is the actual value. Make sure you know what you're looking at. So the scatter plot itself is the actual data. The red line is the prediction. Everybody understanding so far what I'm talking about here? Which one's the prediction? The red line or the dots? Red line. The dots would be actual data. Okay. What then would be the predicted price of a vehicle 70,000 miles driven? Well, you just did that. It would be how much? Not 30,000. What would be the predicted price? If the actual is 70, 21, the prediction is 70, 26. What does that actually mean? The predicted price would be when you take into account that these are counting in thousands. The predicted price would be 26,000. Now, how do we get that? Because this 26 is in, what units is it in? Thousands. Okay, so make sure we add that to the note. The predicted price for a vehicle with 70,000 miles driven is $26,000. Now, what I want to make sure you know is this over here is called a scatter plot. This is a scatter plot over here. This is a residual plot. So if that's a scatter plot, this is a residual plot. What does that mean? This shows you how far off each value is. So I want you to go over here. What is the X value of this point right here? This point. What's the X value? 70. Good. So the predictant is 70. Now, notice that over here our numbers are 21 and 26. Now, I want you to look and see what's the Y value at that point. What is the Y value at that point? I'll make it easier. I'm going to add in a line this way.
-5.
It's -5. At 70, it's a -5. Now, why would this make sense? Do you remember the formula I gave you on the previous page about residuals? Do you remember what the formula was for residuals on the previous page? I told you need to know it. It's Y minus Y hat. So the residual is the actual minus, it was the actual, which is Y minus the predicted, which is Y hat. In this case, the residual, I'm just going to say R, would equal, what was our actual data? The 21, remember it's Y. It's not X and X hat, it's Y and Y hat. The actual is 21 minus the predicted, which was 26. You got it. I don't know what's going on. My board froze up on me here. There it goes. Which is 26. What is 21 minus 26? -5. Notice that's where that -5 comes from. That makes sense how the residual plot works? So the residual plot shows you how far off each point is. That's what that does. Okay, so that's going to be something we're going to be using throughout the year as well. So why use residuals? A residual, again, this is to help you out when I'm not here more than anything when you look at this at home. A residuals can assess whether a regression model is appropriate by saying when you look at it, you can tell whether it's a good model or a bad model. This is actually a great model. The reason it's a great model, listen to me, listen closely. When you look at the residuals, do they look totally randomly scattered, or does it look like there's a pattern in how they're scattered? You say those residuals over here, do they look totally scattered, like just randomly scattered around? Or do you say there's a pattern? There's an even amount on both sides. Does it look like a U? Does it look like an S curve? Does it look like a line? Or does it just look like there's a bunch of random dots? If it looks random, it means it's a great model. Because what that means is the line is going through pretty evenly. If there was a pattern, that means you chose the wrong equation. Because there was an equation and your prediction's going through them the wrong way, like it's supposed to be a U, but you're going through them like a line. That everything, you would be a pattern to how much you were missing. You'd be able to say, oh, I'm consistently off a certain amount. That means you consistently chose the wrong equation. Does that make sense? Over here, does it look like I'm consistently off, like a pattern, or does it look like I'm totally randomly off? This one I'm a little under, this one I'm over, this one I'm under, this one I'm over. See how it seems split? That means we chose a good model because our model is right in the middle of the values. Does that make sense? So you want a residual that looks scattered like this. So that's the first thing. Second, a scatter plot. It says here it changes the y values, whereas the x values stay the same. So a scatter, it makes sense though. A residual should be showing you the y values with the x's staying the same. Why is that? Because what's the formula for a residual? Actual minus predicted, which is y minus y hat. You're changing the y's, you're not changing the x's. You see how the x's stay the same? But did the y's stay the same? No, that's what changes. Determine whether a regression model is appropriate, you look for the patterns. That's what I was telling you here. If there is no pattern, the regression model is appropriate. If there is a distinct pattern, the regression model is not appropriate. So you don't want a pattern on a regression. Do you want a pattern or do you not want a pattern? You do not want a pattern. That's very important you know that. Okay, so let me show you some. Below to the left, we have a scatter plot. Just to make sure everybody's following, put scatter plot up at the top. Below to the left, we have a scatter plot showing the relationship between the Super Bowl number and the cost of a 30-second commercial for the years from 1967 to 2013. Note that this is 1967. This right here is 2013. Actually, if I added 45, that wouldn't be 2013. So 2013 is going to be the last right there. Yeah, because we need to add 46. So it should be pointing just after the 45. That's 2013. Along with the least squares regression line. So here's my regression line, the R squared values basically. The resulting residual plot is shown to the right. Now this is a residual plot. So go to the top. I want you to put residual plot. So just to make sure you're following along with what these represent, this is my residual plot. Look at your x's. Are the x's the same or different? The x's are the same. So this would be the year 1967. And 46 would be the year 2013. Now, check out the y's. Are the y's the same or are they different? Different, because what is the formula for a residual? Yeah, so the residual is equal to y minus y hat, which means the y's change. The y's change. It's the actual y minus the predicted y. Okay, now look at this residual plot. Does it look randomly scattered or do they look like they're consistently wrong? Meaning you can predict how they're going to be wrong. You see how they're consistently wrong? Like, for example, if I just told you, hey, plot a point at 45, do you think you have a pretty good idea? Plot a point when the x is 45. Do you think you have a pretty good idea where to plot that point? Are you going to plot the point down here? Would you say, oh, here's 45, I'll plot it right there. Is that where you would plot that point? Would you have a pretty good idea where to plot it? Now, why would you have a pretty good idea where to plot it? you would look at it and say, oh, it looks like there's a pattern here. You see how it looks like kind of like a parabola here? That means this is a bad model. This is a bad model. This situation or this scenario, whatever you want to say here, used a linear model. How do I know it's linear? Look over here at the predicted. What kind of shape is that red line right there? The predicted. What did they use? A line, a parabola, a S-curve, a line. Now, this scenario used a linear model, which was not appropriate. How do I know it's not appropriate? Since the residuals, now you're looking over here, formed a pattern or did not form a pattern? Formed an obvious pattern. Therefore, it's a linear model is not appropriate. Okay, so this would not be inappropriate. Now, I can tell you right now, I can look at it. You're going to learn that's called exponential. We should have used an exponential model. So we would use the wrong model. So you need to know whether or not you're picking a good model or a bad model. How you know is you look at the residuals and you see you're looking for, is there a pattern or are they randomly scattered? You're wanting the residuals to look randomly scattered. The smaller, the closer and closer and closer all the points are to the line, the better they are. The farther and farther apart or the more of a pattern, the worse off you are. So you want as close to that red line as possible. As far as the Y's go, you want small amounts of Y changing, and you don't want a pattern. That's what you're looking for when you look at a residual. All right. So I just answered this part right here. This would be the answer. Is a linear regression model appropriate for this data? It's not appropriate since the residuals form an obvious pattern. That's the explanation. Now, I gave you the answer to part B. When you look at it, let's talk about what each of these shapes are. It says, if not appropriate, consider what would be more appropriate. Now, a quadratic, what does a quadratic look like? What shape is a quadratic? A parabola. Draw a parabola here under quadratic. What shape, Thomas, is a cubic function? An S. A rational usually is two pieces. Giovanni, what kind of shapes does a rational usually look like? Not V's, that's absolute value. Asif's got it, yeah. Not S curves, I call them C curves. It usually looks like C curves. Some people call them L's. And exponential. Exponential looks like an airplane taking off. Okay, now when you look back at the data, the actual data on the scatter plot, what does it look like? Exponential. So here we'd say an exponential model appears to be more accurate from the data in the scatter plot. Now, I would not know, what did I just do? I would not know about the residuals because I don't have a residuals for a exponential model. The residuals they gave us were for the linear model. Okay, so the residuals that they gave us was from that linear model. I don't know what the model would look like, the residuals for exponential, but I could just say an exponential model appears to be more accurate from the data in the scatter plot. That's all I can say there. Julian, hanging in? Okay. All right. Now, let's go on to example 4 here. It says here, the Texas Department of Public Safety discovered that the relationship between the speed and stopping distance can be appropriately modeled by a quadratic regression model. Which residual plot would support this conclusion? Which one, if you were looking, these are residuals. Make sure you're following on both of these. These are residuals. That's a residual graph. This is a residual graph. Which one would be saying it's an appropriate model? Which one would be saying it's not appropriate model? A is appropriate. Why is A appropriate?
They're random.
They're random. B would be not appropriate. Why not appropriate?
Single pattern.
Not appropriate since there exists an obvious pattern. So if we said, hey, this was a quadratic model and it was a good model, then this must have been the residual. That would have been the residual. Everything's randomly scattered. Now, why would that mean this is good? I'm going to talk over it one more time. Why it's saying it's good? Is it saying like this point? Remember, the prediction is the middle line. I don't know if I said that on a residual. When you see a residual, the predicted line is the red. So if this is the prediction on a scatter plot, this was a linear, so it has a linear prediction. On a residual, it's always a line. That's just showing you that this is the predicted values. Remember, the equation is y minus y hat. So if the actual is above, it goes above it. If the actual is less than the predicted, it goes below it. So a residual will always have a flat line across. What this is saying is that we have some points where my predicted value is greater than the actual. We have others where the actual is greater than predicted, and it's randomly scattered. That means sometimes it's right on the money. Sometimes the predicted is a little bit too small. Sometimes it's a little too high. But either way, it's just kind of spread out evenly. So it's a pretty good model because you're always within a certain range. You can predict the values pretty accurately. You know that you're going to be within a certain range. Over here, I'm not predicting wells. I have a pattern here. All of these, I'm predicting too high. I'm predicting too high. Over here, I'm always predicting too low. Over here, I'm always predicting too high. There's no pattern to it. I mean, because there is a pattern, it's not appropriate. That's what I meant to say. It's not appropriate because there's always a pattern to how I'm missing. So now let's go back to example 1. So what I want you to do in your calculator here, press the home screen. I want you to hit browse, number 2. Home screen, choose browse. And in here, we saved something. Do you remember how we saved it as, I think it's in My Documents. Click My Documents. We saved it as document 1. Oh, maybe it's down here. Let's see, where is it? Document 1, there it is. Do you see it? Go ahead and choose it. Do you want to save unused? I'm going to hit no. What I've been working on, I can erase. I don't need it anymore. So I'm going to hit no. And it brings back up our table. Remember, we had the time, the amount of weeks, and the weight of a baby. That's what we had here. What we want to know now is what is the residual of a baby that's 5 weeks old. So here's how you do that. Again, press Control Doc. This is going to give us a new page. Control Doc. And from here, for define residuals, you're going to go to Data and Statistics. So choose Data and Statistics. Come on, Marcus. Now, what you're going to do is down the bottom, it says click to add a variable. Click on the x-axis. Which variable was our x? Do you remember? It was t. Choose t there. Now, on the y-axis, we're not going to choose the weight. The w would show us the actual point. I want the residual. So if you look through here, I want you to go to stat.resid. Now, I'm not sure what this stat resid is, but I'm going to go to the very first one. You see how it says residual? And this shows us how our data is missing, how our data is viewed. Okay, so based off of this, did y'all choose stat.resid? That's the residuals based off of our values here. I'm going to go Tools. I'm going to capture this, move it over to our documents. Okay. What is the residual of a baby that's 5 weeks old? All right, so let's look on here. The residual when a baby is 5 weeks old. You're trying to figure out what is that point. Now, does it let you select yours? Yeah, it does. Let me see if I can highlight yours so you can keep the value up. And I'm just going to take a picture of mine here and add it in. See if that works. Okay, so that's the value I'm getting. Are you getting the same value there? Are y'all getting that? Yeah? Okay. So mine's not looking too good anymore, but I'm trying to add it in. There it is. So what is the residual of a baby at 5 weeks old? So on the residual is the Y value. Remember it not, you don't, residual at 5 weeks is equal to negative 0.07. So what does that mean? We're off by that much. That's correct. Now, how are we off? Is our prediction too high or is our prediction too low? Remember, the flat line is our prediction. Is our prediction too high or is our prediction too low? What do you think? It's too high. Very good. Our prediction is too high. How do we know it's too high? Because when you look at it, here's the prediction. Guess what the prediction is? You see how the prediction's above it? So I want to say the predicted value is 0.07 kilograms. That's what we were in. The predicted value is 0.07 kilograms too high or too great, whatever word you want to use. Another way of saying it is the actual baby weight is 0.07 below kilograms, kilograms below the predicted weight. Right. Okay. Any questions on how I got that value or what that means? Remember, the residual is the actual minus the predicted. Okay, if a baby that is 7.5 weeks old has a residual of negative 0.7 kilograms, what was the actual weight of the 7.5 week old baby? So let's make sure we understand the formula again. The T is 7.5. That's what we know. The T is 7.5. We also know the residual here. The residual is negative 0.7. What's the formula, though, for residuals? Okay, so the y minus y hat is equal to negative 0.7. Does that make sense? Okay, so how could we actually find out the baby? Well, we could use our equation to find out what the predicted value is. So come back over to our data. See, 7.5 is not on here. You see how 7.5 is not on our residual here? It's not there. So we need to find out what that value is. I'm going to go over to the tab that's already 1.3, that's already open. And let's find out what's the predicted weight at 7.5 weeks. How could I find the predicted weight at 7.5 weeks? You remember what we typed in earlier? F1, parentheses, 7.5. If I type that in, that's going to give me the predicted weight at 7.5. And I'm getting 4.9325. Y'all getting the same values? All right, great. So I want to add that back over. All right, if my predicted weight at 7.5 is 4.935, now I could say that y minus 4.9325 is going to equal negative 0.7. We could do an insolve on this, but this one's such easy algebra. What's the only step left to get my to solve this equation here? What would I need to do to get y isolated here to find my actual data? All I'm going to do is add this. That's going to be such an easy. Again, you could round your value. I didn't round this one just because if I added one decimal, I'd have the exact number, so I just left it. I'm going to add that. So I'm going to take this number that I just got, and I'm going to subtract 0.7 from it. That's the same thing. 4.9325, that's a positive 4.9325, and I'm subtracting 0.7, and I got 4.2325. That's my value there. That's my actual value. Let me scroll this up a little bit so you can see it better. So the actual value is 4.2325. The actual weight of a baby at 7.5 weeks is 4.2325 kilograms. No, please. All right. So you've seen me do a lot of little things with the calculator. You've seen residuals. You've seen all kinds of stuff. It's your turn to try one. DOL number one. I'll let you use that table. And hey, you know, one more thing I haven't shown you yet. I want to show you one more thing before we go off this. Before we go, real quick, before you clear, you're not going to need this example again. We can clear our calculators in a second. I want you real quickly press Control Doc, Control Doc, hit Data and Statistics. Control Doc, Data and Statistics. We've done this before. Click on the X variable, click on the add a variable. Click T down there. So you'll always put the X value here. It's a matter of, in my class, what you're choosing for Y. If you had no idea what the model was, what I would suggest you do is then you hit W, the Y value, and you can at least see what it looks like the model should be. What did this, when you look at these dots, what does it look like it should be? Does it look like it should be linear, or does it look like it should be quadratic? Does it look exponential? What does that look like to you if you were to guess? Linear. Yeah, if you don't know a model, use the scatter plot. That's how you get a scatter plot, is you would do data, what was this called? Data and I forgot. What was it called? Control Doc. Data and statistics. Yeah, use data and statistics if you're not sure. You can make a scatter plot. That's what I did there. If you just do the actual values, it's a scatter plot. Or you could do T and the residual if you want to see the residuals. That's the difference there, okay? So you'll need that on your DOL here. As you work on your DOL, type those in. And then I would add a document and do a scatter plot, which means you're going to use your X variable and your Y variable and to see what type of model you think it should be. Okay, DOL number one. All right, picking back up here. We have one more equation to take a look at. So it says here, a table of ordered pairs is shown. What I want to do first is type this in. So let's go home screen, new document. And you can say, do you want to save changes? Hit no, you don't want to save that, just delete it out of there. I want you to add lists and spreadsheets. Now this one they title X and Y, so let's just go up and put in our X variable and our Y variable. We'll type in the points. All right, I typed in the X variables. Now I'm going to come back and type in my Y variables. My Y values, I should say, not variables, my values. Okay, on this problem, it says using a logarithmic regression. So I know we haven't covered logs yet, but it's telling us what to use. We're going to choose a logarithmic regression. Write an equation in this form. Okay, so press menu, statistics, Stat calculations. They're telling us we don't have to look at the scatter plot to figure out what type of model. We're going to go down until you see logarithmic. It's probably going to be letter B. It's probably going to be after exponential. Yeah, it's B. Choose logarithmic. For the x list, what variable did we type in for our x's? X. And what variable did we type in for y's? Y. Once again, it's going to be saving it as F1 because I cleared my calculator. You can just press enter from there, by the way. If you press enter twice, it'll give you your answer. I'm going to go up, and remember, the R squared tells you how accurate it is. This is saying 0.99. This is random here. How accurate does it mean if it says 0.99?
Very
It's extremely accurate. What's a perfect answer?
100.
Not 100, but 1. 1 would be 100. Okay, I'm going to take a picture here where you can see the equation so we know where our variables go. Since we have not dealt with this equation before, I want to make sure we don't make a silly mistake here. All right, so when I copy this over, it says, write a model f of x equals a plus b the x. A needs to be the constant. When you look in your calculator, check, is a the constant? The way they built their equation, is a variable the constant? Yes, it is. Okay, so a is the correct constant, so our model would be f of x equals, I'm going to do 3 decimals. So a is 2.863 plus our b, again, 3 decimals, 1.818, and this says natural log of x. Y'all don't know what natural log is, but just put it in. There's our equation. All right, on the next slide, it says the residual plot is provided. What are the coordinates of the point R on the graph? So how could I get to my residual plot on our calculator? What would we do? Hit Control Dot, data and statistics. You always, always, always will put the x variable on the x-axis. So choose x there. Now, if you want a residual, what do we click for the y-axis in this case? Stat.resid. I'm just going to click the first one. I'm not sure why it has a stat.3. I'm not sure what that means. There's my residual plot. If you click this button, or click that point right there, it should give you your values. Is there a way to, let's see here. J, let me see if that works. And J. Perfect. All right, so there's my point. What are the coordinates? Well, there's the coordinates right there. I'm going to list it out as 3 decimals. So R would equal 1.6, comma, negative 4.18. I'm just going to do 3 decimals like that. That would be the value of R right there. Any questions over that? How I got that value? No? Did y'all all get the same value as me? Okay, great. Does the residual for the point R indicate that the model F underestimates or overestimates? Okay, you need to remember this. This line, is that the actual line or is that the predicted value? The predicted. Did the predicted over or underestimate? Over. It's over it. The predicted, the model F overestimates the actual value by that actual value of y by 0.418 at the x value 1.6. There's your translation to make sense of what we just did right there. And with that, we'd have one more DOL for you to figure out.